Physics Part 180. The waves interfere, producing a wave pattern, as shown in the figure, in which the crests and the troughs do not move. This pattern is called a stationary wave or a standing wave. Because it does not move, a stationary wave is the result of interference between two waves of equal frequency and amplitude, traveling along the same line with the same speed but in opposite direction. The stationary waves on strings. If a string is plucked and allowed to vibrate freely, there are certain frequencies at which it will vibrate. The amplitude of the vibration at these frequencies is large. This is known as resonance effect. It is possible to investigate stationary waves in a more controlled manner using a length of string under tension and a vibrator driven by a signal generator. Vibrator driven by a signal generator. As the frequency of the vibrator is changed, different standing wave patterns are formed. Some of these are shown in the figure. The figure shows the simplest way in which stretched string can vibrate. The wave pattern has a single loop. This is called the fundamental mode of vibration, or the first harmonic one. At the end of the string there is no vibration. These points are called nodes. At the center of the string the amplitude is a maximum. A point of maximum amplitude is called antinode. Nodes and antinodes do not move along the string. They stay stationary, and that's what we call them, the stationary waves. The wavelength of lambda of the standing wave in the fundamental mode is 2L. From the wave equation, C is equal to F into A. The frequency of the node produced by the string vibrating in its fundamental mode is given by F1 is equal to C over 2L, where C is the spread of progressive waves which have interfered to produce the stationary wave. The figure shows the second mode of vibration of the string. The stationary wave pattern has two loops. This mode is sometimes called the first overtone or the second harmonic. Don't be confused. The wavelength of the second mode is L. Applying the wave equation, the frequency F2 is found to be C over L. The figure shows the third mode, the second overtone, or the third harmonic. This is a pattern with three loops. The wavelength is 2L over 3. The frequency is F3 is 3C over 2L. The third mode of vibration of a stretched string. The general expression for the frequency of Fn of the nth mode or the nth harmonic or n-1 overtone is Fn is equal to Cn divided by 2L. N is equal to 1, 2, 3. The key features of a stationary wave pattern on a string which distinguish it from the progressive wave are as follows. The nodes and the antinodes do not move along the string, whereas in a progressive wave, the crests and the troughs do move along it. The amplitude of the vibration varies with the position along the string. It is 0 at a node and maximum at an antinode. In a progressive wave, all points have the same amplitude. Between the adjacent mode, all points of the stationary wave vibrate in phase. that is, all particles of the string are at their maximum displacement at the same instant. In a progressive wave, phase varies continually along the wave.